Since the dawn of humanity, we have looked up at the stars with a blend of awe, curiosity, and wonder. The sky has been a canvas of mystery, sparking questions about our place in the universe and what lies beyond. Human beings have an inherent drive to explore, pushing boundaries both physical and intellectual. This curiosity propelled ancient sailors across uncharted seas and sent explorers to the far reaches of the Earth. Today, it inspires us to look to the stars, dreaming of interstellar exploration, of crossing the unimaginable distances between our solar system and others, to uncover what or who may be out there. This curiosity has evolved into something even more powerful, a collective ambition to expand our reach beyond the bounds of Earth and our solar system. Over the last century, space exploration has shifted from a distant dream to a tangible reality. From the first human orbit around Earth to the historic moon landings, and the recent triumphs in robotic missions to Mars, each milestone represents humanity's steady march toward understanding the cosmos. However, interstellar travel presents a level of challenge that far exceeds anything we faced before. It isn't merely about reaching another planet or sending probes to distant moons. It's about crossing light years, vast stretches of space that could take decades, if not centuries, to traverse, even with advanced technology. Despite the obstacles, the lure of exploring other star systems and potentially habitable worlds drives scientists, engineers, and visionaries to find solutions that might one day bring interstellar travel within reach. One of the most intriguing destinations within our cosmic neighborhood is Proxima Centauri b, a planet orbiting the closest star to our sun, Proxima Centauri, located about 4.24 light-years away. This exoplanet has captivated the scientific community because it lies within the habitable zone of its star, where conditions may be suitable for liquid water to exist on its surface, an essential ingredient for life as we know it. The discovery of Proxima Centauri b ignited excitement worldwide, sparking hope that this relatively nearby planet might one day be accessible. While we currently have no means of reaching it within a human lifetime, the concept of a habitable planet so close to our solar system presents a tantalizing target for future missions. For scientists, Proxima Centauri b has become a symbol of possibility, a celestial body that represents humanity's next great leap. If we can overcome the challenges of distance and develop technology capable of such journeys, Proxima Centauri b could serve as our first foray into the wider universe. But while Proxima Centauri b feels relatively close in astronomical terms, the challenges of reaching it are daunting. The distance between Earth and Proxima Centauri b is approximately 25 trillion miles, 40 trillion kilometers. At the speed of current spacecraft, it would take tens of thousands of years to reach this star system. This enormous distance highlights the technological and logistical hurdles we face in making interstellar travel feasible. Traditional propulsion systems, such as those used in rockets today, are far too slow to reach another star system within a practical time frame. Even the fastest probes launched so far, like Voyager 1, are traveling at only a fraction of the speed needed to make an interstellar journey within a human lifetime. To reach Proxima Centauri b, we would need to develop revolutionary propulsion technologies, such as light sails powered by lasers or nuclear fusion engines, that could propel spacecraft at a significant fraction of the speed of light. Moreover, there are practical considerations beyond propulsion. We would need to ensure that any interstellar spacecraft is capable of surviving extreme conditions over decades or even centuries. The spacecraft would have to be self-sustaining, capable of handling potential impacts with micrometeoroids and cosmic radiation, and able to communicate across vast distances without significant degradation in signal quality. These challenges require breakthroughs not only in engineering but in materials science, physics, and our understanding of long-duration life support systems. However, these technological obstacles also drive innovation, leading scientists to explore radical new ideas and technologies that, while currently theoretical, may one day make interstellar travel a reality. As we imagine what it might take to reach Proxima Centauri b, we're reminded of the journey humanity has undertaken since we first gazed at the stars. Interstellar exploration is not simply about technological advancement. It's about our innate desire to know the unknown, to bridge the gap between curiosity and understanding. This pursuit speaks to the essence of human nature. We are explorers, unafraid to confront the unknown, if it means expanding the limits of our knowledge and potential. Framing the journey to Proxima Centauri b in this light transforms the mission from a purely scientific endeavor to a philosophical one. It's not just about reaching another star, it's about expanding the boundaries of what we consider possible. Every step we take in the direction of interstellar travel, from understanding propulsion to learning about life support systems for long-haul missions, is part of a larger journey, a journey that reflects our deepest aspirations and our drive to achieve what has long seemed impossible. In a way, Proxima Centauri b serves as a beacon for all of humanity, a distant yet attainable goal that calls on us to stretch our technological capabilities and think beyond our current limitations, just as explorers of the past set sail into uncharted waters. The quest to reach another star system asks us to navigate the uncharted realms of deep space. This ambition to reach out into the cosmos, to bridge the gulf between stars, is a testament to human resilience, ingenuity, and our undying curiosity. As we begin this journey into the world of interstellar exploration, we do so with the understanding that it is a monumental task, one that may take generations to achieve. Yet, with each small step forward, we inch closer to the stars and to fulfilling one of humanity's oldest and most profound dreams, to touch the very fabric of the universe and discover what lies beyond our familiar horizons. The journey of humanity into space is a tale of courage, innovation, and relentless ambition. Beginning in the 20th century, space exploration was initially a response to the geopolitical tensions of the Cold War, yet it quickly evolved into a global quest to unlock the mysteries of the cosmos. From the first tentative steps into Earth's orbit to the groundbreaking Apollo moon landings, and the pioneering Voyager missions that ventured into the interstellar unknown, each milestone has represented a leap forward in our understanding of the universe and our place within it. These early accomplishments laid the foundation for modern space exploration, inspiring future generations to look beyond our world. Space exploration began in earnest in the late 1950s, as technological advances and global competition spurred the Soviet Union and the United States into a race for dominance beyond Earth. On October 4, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite, into orbit around Earth. Weighing just 83.6 kilograms and measuring less than 2 feet in diameter, Sputnik 1 was a modest feat in comparison to later missions. However, it was a groundbreaking achievement that demonstrated the possibility of sending human-made objects into space. This achievement sparked a mixture of excitement and apprehension around the world, marking the dawn of the space age. The Soviet Union continued its pioneering efforts with the launch of Laika, a stray dog from Moscow streets, aboard Sputnik 2 on November 3, 1957. Laika became the first living creature to orbit Earth, and though her mission was one way, it provided valuable insights into the biological effects of space travel on living organisms. These initial missions underscored the immense challenges of space travel, highlighting the physical and environmental stresses that future human astronauts would need to endure and survive. In response, the United States ramped up its space program under NASA, which had been established in 1958 to lead American efforts in space. NASA's first successful satellite launch, Explorer 1, occurred on January 31, 1958, carrying scientific instruments that discovered the Van Allen radiation belts around Earth. By the early 1960s, the space race was in full swing, with both superpowers striving for new milestones. On April 12, 1961, Soviet cosmonaut Yuri Gagarin became the first human to journey into space, orbiting Earth aboard Vostok 1. Gagarin's 108-minute flight was a monumental achievement, not only for the Soviet Union but for humanity. His courage and the technical mastery required for the mission inspired people worldwide, demonstrating that humans could survive and work in the harsh environment of space. Gagarin's iconic words, "I see Earth. It is so beautiful," captured the spirit of human exploration and cemented his legacy as a pioneer of space travel. The United States followed with its own achievements. On May 5, 1961, American astronaut Alan Shepard became the first American in space aboard Freedom 7, although his flight was suborbital. Later that year, John Glenn's orbital mission on Friendship 7 in 1962 marked the United States' entry into Earth orbit, solidifying its place in the space race and paving the way for future human missions beyond Earth's atmosphere. The Apollo program represented the pinnacle of early human space exploration and showcased humanity's capacity to achieve seemingly impossible goals. Initiated in 1961 by U.S. President John F. Kennedy, the Apollo program's primary objective was to land a human on the moon and return them safely to Earth. The Apollo missions were driven by political ambition and a desire to assert American technological superiority, yet they transcended these motivations to become a symbol of human ingenuity and bravery. The Apollo program's first triumph came in 1968 with Apollo 8, the first mission to orbit the moon. Frank Borman, Jim Lovell, and Bill Anders were the first humans to witness the Earth rising over the lunar horizon, a view that forever changed perspectives on our planet's fragility and unity. Anders' photograph of Earth rays became an iconic image that fueled the environmental movement, reminding people that Earth is a small, interconnected home in the vastness of space. On July 20th, 1969, NASA achieved its crowning accomplishment when Apollo 11 successfully landed on the Moon. As Neil Armstrong descended from the lunar module and took the first human steps on the Moon's surface, he uttered the immortal words, "That's one small step for man, one giant leap for mankind." Armstrong and his fellow astronaut, Buzz Aldrin, spent a total of 21 hours on the lunar surface, collecting soil and rock samples, conducting experiments, and deploying scientific instruments. These samples provided scientists with new insights into the Moon's composition and geological history, helping them piece together the story of our nearest celestial neighbor. The Apollo program continued with several more missions, including Apollo 12, Apollo 14, and Apollo 15, each of which expanded scientific exploration on the Moon. The later missions were particularly significant for their geological findings and extended stays on the lunar surface. Apollo 15, for instance, introduced the lunar rover, which allowed astronauts to cover greater distances and collect samples from diverse areas of the Moon. This era of lunar exploration concluded with Apollo 17 in 1972, marking the end of direct human exploration of the Moon and shifting the focus back to Earth orbit and robotic missions. The Apollo missions had an enduring impact, not only advancing our scientific understanding of the Moon, but also transforming humanity's perception of space. They served as a testament to what could be accomplished when knowledge, resources, and determination were focused on a shared goal. The Apollo program's legacy continues to inspire space programs worldwide, fueling interest in returning to the Moon and even setting sights on Mars. As the Apollo program came to an end, NASA turned its attention to more distant destinations within our solar system and beyond. The Voyager program, launched in 1977, was an ambitious effort to explore the outer planets and the boundaries of the solar system. The twin spacecraft, Voyager 1 and Voyager 2, were designed to take advantage of a rare planetary alignment that occurs only once every 176 years, enabling them to visit multiple outer planets using gravity-assist maneuvers. Voyager 2 was launched on August 20th, 1977, followed by Voyager 1 on September 5th, 1977. Although launched later, Voyager 1 was placed on a faster trajectory and soon overtook its twin. Both spacecraft were equipped with a suite of scientific instruments, cameras, and sensors to study the atmospheres, moons, and magnetic fields of the gas giants they encountered. The Voyager missions provided humanity with its first close-up images of Jupiter and Saturn, revealing complex atmospheric systems, giant storms, and unique moons that were previously only distant points of light. Voyager 2 went on to explore Uranus and Neptune, making it the only spacecraft to visit these ice giants to date. These flybys unveiled the diversity of moons, including active volcanoes on Jupiter's moon Io, geysers on Neptune's moon Triton, and the thick haze surrounding Saturn's moon Titan. One of the most remarkable aspects of the Voyager missions was the inclusion of the Golden Record, a phonograph record containing sounds, music, and images from Earth, intended as a message for any extraterrestrial civilization that might encounter the spacecraft. Curated by a team led by astronomer Carl Sagan, the Golden Record encapsulated the essence of life on Earth, from greetings in multiple languages to music by composers like Bach and Beethoven, along with the sounds of nature. This message, immortalized on both Voyagers, represents humanity's hope to connect with intelligent life beyond our solar system. In 1990, as Voyager 1 was about to leave the solar system, mission controllers directed it to turn its camera back toward Earth, capturing the now famous pale blue dot image. In this photo, Earth appeared as a tiny speck against the vastness of space, a poignant reminder of our small place in the cosmos. Carl Sagan eloquently described the image, noting that every human being who ever lived on a mote of dust suspended in a sunbeam. This image continues to inspire reflections on the interconnectedness of humanity and the fragility of life on Earth. Today, Voyager 1 and Voyager 2 continue their journey into interstellar space, having crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins. They are the most distant human-made objects from Earth, carrying the hopes and dreams of humanity with them. The Voyagers symbolize the indomitable spirit of exploration, embodying the idea that human curiosity knows no bounds and will continue to push outward into the universe. The discovery of exoplanets, planets that orbit stars outside our solar system, has transformed our understanding of the cosmos. Just a few decades ago, scientists had no proof that planets existed beyond our sun. Today, thanks to groundbreaking technological advancements and observational techniques, we know of thousands of exoplanets, each offering a potential glimpse into worlds that may harbor life or reveal new insights about planetary systems. Among the most intriguing of these is Proxima Centauri b, an exoplanet orbiting the closest star to our own, Proxima Centauri. This discovery has fueled hope for future exploration and reignited questions about the diversity of planetary systems in the universe. The discovery of exoplanets, planets that orbit stars outside our solar system, has transformed our understanding of the cosmos. Just a few decades ago, scientists had no proof that planets existed beyond our sun. Today, thanks to groundbreaking technological advancements and observational techniques, we know of thousands of exoplanets, each offering a potential glimpse into worlds that may harbor life or reveal new insights about planetary systems. Among the most intriguing of these is Proxima Centauri b, an exoplanet orbiting the closest star to our own, Proxima Centauri. This discovery has fueled hope for future exploration and reignited questions about the diversity of planetary systems in the universe. Proxima Centauri, the closest known star to our sun, is part of the Alpha Centauri star system. This system consists of three stars, Alpha Centauri A and Alpha Centauri B, which are a pair of sun-like stars orbiting each other, and Proxima Centauri, a red dwarf star that orbits the pair from a more distant position. Located only 4.24 light-years away, Proxima Centauri is, by cosmic standards, our closest stellar neighbor, making it an object of intense study and curiosity. In 2016, astronomers announced the discovery of an exoplanet orbiting Proxima Centauri, aptly named Proxima Centauri b. This planet lies in the habitable zone of its star, the region where temperatures could allow for liquid water to exist on the surface. Although Proxima Centauri b orbits its star at a much closer distance than Earth orbits the Sun, it receives comparable warmth due to Proxima Centauri's relatively cool temperature as a red dwarf. This discovery was groundbreaking, as it brought us face to face with the tantalizing possibility of a potentially habitable planet just beyond our solar system. Proxima Centauri b has a mass slightly greater than Earth's, indicating it may be a rocky planet. While the exact conditions on its surface remain unknown, scientists are hopeful that Proxima Centauri b could support water in liquid form, an essential requirement for life as we know it. However, being in orbit around a red dwarf star also presents unique challenges. Proxima Centauri emits high levels of stellar flares and radiation, which could strip away the atmosphere of a close-orbiting planet like Proxima Centauri b over time. This raises questions about the planet's potential to retain a stable atmosphere capable of shielding and supporting life. Despite these challenges, Proxima Centauri b's proximity makes it a prime candidate for further study. Scientists have proposed ambitious missions such as the Breakthrough Stars HOT initiative, which aims to send small, light sail-propelled probes to explore this neighboring star system. Such missions, while still theoretical, illustrate the immense potential of Proxima Centauri b as a target for humanity's first interstellar exploration. Proxima Centauri b represents more than just an object of scientific curiosity. It symbolizes the prospect of reaching out beyond our solar system and discovering an entirely new world. The discovery of Proxima Centauri b, along with thousands of other exoplanets, was made possible by advanced methods of observation, particularly the radial velocity and transit methods. These techniques have allowed astronomers to identify planets that would otherwise remain invisible, as exoplanets do not emit their own light and are often lost in the brightness of their parent stars. The radial velocity method, also known as the Doppler method, detects exoplanets by observing subtle shifts in a star's spectral lines. When a planet orbits a star, the gravitational interaction causes the star to wobble slightly. As the planet pulls the star in one direction, the star moves closer to us, compressing the wavelengths of its light, a phenomenon known as the Doppler shift. When the star moves away, its light stretches to longer wavelengths. By analyzing these shifts, astronomers can infer the presence of an orbiting planet, as well as its mass and distance from the star. The radial velocity method was one of the first successful techniques used to discover exoplanets, including the famous discovery of 51 Pegasi b in 1995, the first confirmed exoplanet orbiting a sun-like star. This method has been particularly effective for identifying larger exoplanets, like gas giants, that exert a significant gravitational force on their stars. Proxima Centauri b was also detected using the radial velocity method, as its gravitational influence on Proxima Centauri creates a measurable wobble, revealing clues about its mass and orbit. The transit method, by contrast, detects exoplanets by observing the dimming of a star's light as a planet passes or transits in front of it. When a planet moves between its star and the observer, it temporarily blocks a small portion of the star's light, causing a slight dip in brightness. By measuring these dips, astronomers can determine the size of the planet and estimate its orbital period. If multiple transits are observed, scientists can gather additional data about the planet's size, atmospheric composition, and sometimes even its temperature. The transit method has been particularly successful in identifying Earth-sized exoplanets, as it allows scientists to measure their size and orbital distance with high precision. The Kepler Space Telescope, launched in 2009, used the transit method to observe over 150,000 stars in a single region of the sky, leading to the discovery of thousands of exoplanets. Kepler's findings expanded our understanding of the diversity and abundance of exoplanets, showing that planets come in a wide range of sizes, compositions, and orbital configurations. The transit method has an additional advantage when a star's light passes through the atmosphere of a transiting planet. It interacts with the gases in the atmosphere, causing certain wavelengths to be absorbed. By studying these absorption patterns, known as transmission spectroscopy, scientists can deduce the chemical composition of an exoplanet's atmosphere. This method has been used to identify gases like water vapor, methane, and carbon dioxide in the atmospheres of some exoplanets, providing essential clues about their potential habitability. Together, the radial velocity and transit methods have revolutionized our understanding of planetary systems beyond our own. These techniques, along with the development of space telescopes like Kepler and its successor, the Transiting Exoplanet Survey satellite tests, have ushered in an era of exoplanet discovery that would have been unimaginable just a few decades ago. The discovery of exoplanets has had a profound impact on humanity's perspective of the cosmos. For most of human history, our solar system was the only known planetary system. Earth, with its unique conditions for life, seemed like a rare oasis in an otherwise empty universe. However, as scientists have identified thousands of exoplanets in diverse environments, our view of the cosmos has transformed. Exoplanets reveal the immense diversity of planetary systems in the universe. Planets have been found orbiting a wide variety of stars, from massive hot blue stars to small, cool red dwarfs. Some exoplanets are gas giants that orbit extremely close to their stars, known as hot Jupiters, while others are rocky, Earth-sized worlds that lie within their star's habitable zone. This diversity challenges our previous assumptions about planetary formation and suggests that the universe may be more hospitable to life than we once believed. The discovery of potentially habitable exoplanets, like Proxima Centauri b, has also raised important questions about the existence of life beyond Earth. If planets with Earth-like conditions are relatively common, it stands to reason that life could arise elsewhere. This idea has spurred a new field of research, astrobiology, which seeks to understand the conditions that support life and to search for biosignatures on distant worlds. Astrobiology has encouraged scientists to develop innovative techniques to detect the chemical fingerprints of life, such as oxygen and methane, in the atmospheres of exoplanets. Exoplanet research also holds profound implications for our understanding of planetary evolution and stability. For example, the discovery of planets in extreme orbits, some with incredibly short orbital periods and others in elongated, eccentric paths, has challenged scientists to rethink models of planetary formation and migration. Exoplanets have been found with atmospheres stripped away by their star's radiation, revealing the effects of stellar activity on planetary environments. By studying these systems, we gain insight into the processes that shape planets and the delicate balance required for a planet to maintain conditions suitable for life. Ultimately, the discovery of exoplanets expanded our sense of place in the cosmos. No longer are we confined to a single planetary system, nor do we view Earth as uniquely special in its ability to host life. Instead, we see ourselves as part of a vast interconnected universe filled with worlds waiting to be explored. Exoplanets represent the possibility that life exists beyond Earth, and they offer us a glimpse into the diversity of environments that nature can create. As we continue to refine our methods and develop new technologies, the study of exoplanets promises to unlock even more secrets of the universe, and may one day lead us to a discovery that redefines life as we know it. The journey to discover exoplanets, particularly ones close to us like Proxima Centauri b, not only reflects our technological achievements but also our enduring curiosity about the unknown. These distant worlds have become symbols of hope, representing the possibility that we may one day find kindred planets, or even life beyond our solar system. They are reminders that our exploration of the cosmos has only just begun, and that each new discovery brings us one step closer to understanding our place in the vast expanse of the universe. As humanity's ambitions expand beyond Earth, the need for advanced propulsion systems becomes increasingly pressing. Our current propulsion technology, while revolutionary in its own right, is insufficient for long-duration interstellar missions. While chemical rockets were powerful enough to take astronauts to the moon, these systems fall far short of the speeds needed to reach even the closest stars within a human lifetime. For interstellar exploration, we require propulsion systems that can achieve far greater speeds, efficiency, and reliability. In this section, we will examine the limitations of current propulsion systems, explore the potential of ion propulsion, nuclear pulse propulsion, and laser propulsion technologies, and assess how these advancements may one day allow us to reach the stars. The propulsion systems currently used in space exploration rely heavily on chemical rockets, which generate thrust through combustion. This method involves igniting a mixture of fuel and oxidizer, creating a high-speed exhaust that propels the spacecraft forward. While effective for launching spacecraft into orbit and conducting relatively short missions within our solar system, chemical rockets are limited by their low efficiency and high fuel requirements. Achieving high speeds requires vast quantities of fuel, which adds significant weight and limits the practical range of chemical propulsion systems. The core limitation of chemical propulsion lies in its relatively low, specific impulse, a measure of the efficiency with which a rocket engine uses fuel. Chemical rockets typically have specific impulses between 200 and 450 seconds, meaning that they consume fuel quickly and require substantial mass to reach desired velocities. For instance, reaching Mars with a crewed mission using chemical propulsion would require carrying large amounts of fuel, which translates to increased costs and complexity. For interstellar travel, where distances are measured in light years rather than millions of miles, chemical propulsion is simply not viable. At best, a chemical rocket might reach speeds of tens of kilometers per second, but reaching even the closest star system, Proxima Centauri, would take thousands of years at these speeds. Moreover, chemical rockets are subject to the rocket equation, a fundamental physics principle that limits a rocket's maximum speed based on its fuel capacity. According to the rocket equation, achieving high speeds requires exponentially increasing amounts of fuel, creating a cycle in which carrying more fuel leads to greater mass requiring yet more fuel. This limitation has driven researchers to explore alternative propulsion methods that are not constrained by the same fuel-to-mass ratio. One of the most promising alternatives to chemical propulsion is ion propulsion, a technology that offers significant advantages in terms of fuel efficiency and longevity. Unlike chemical rockets, ion engines do not rely on combustion. Instead, they use electricity to ionize a propellant, typically xenon gas, and then accelerate the ions to generate thrust. The process begins by stripping electrons from xenon atoms, creating positively charged ions. These ions are then accelerated through an electric field and expelled at high speeds, generating thrust in the opposite direction. The efficiency of ion propulsion lies in its high specific impulse, which can reach several thousand seconds, far exceeding that of chemical rockets. While the thrust generated by an ion engine is relatively low, it is continuous, meaning that over time it can gradually accelerate a spacecraft to extremely high speeds. This characteristic makes ion propulsion ideal for long-duration missions where gradual acceleration is acceptable, such as missions to distant planets or even the outer reaches of our solar system. NASA's Dawn spacecraft, launched in 2007, was one of the first major space missions to utilize ion propulsion. Its mission was to explore the asteroid belt, specifically the protoplanet Vesta and the dwarf planet Ceres. Dawn successfully orbited both bodies using its ion propulsion system to change orbits in a way that would be prohibitively expensive with chemical rockets. The mission demonstrated the viability of ion propulsion for deep space missions, providing valuable insights into the formation of the solar system's smaller bodies. Ion propulsion does have its limitations. The low thrust output means that it cannot be used to launch spacecraft from Earth's surface, where high initial thrust is necessary to overcome gravity. Instead, ion engines are typically deployed after a spacecraft reaches space, where they can gradually accelerate over extended periods. Additionally, ion propulsion relies on a power source such as solar panels or nuclear reactors to generate the electricity needed to ionize the propellant. For missions closer to the sun, solar power is feasible, but for deep space missions, alternative power sources are required, limiting the technology's current applicability. Despite these challenges, ion propulsion remains a key area of research, especially for missions within our solar system. As power generation technology improves, it may be possible to enhance the thrust of ion engines, potentially making them suitable for faster, more ambitious missions. However, for interstellar travel where even higher speeds are necessary, ion propulsion alone may not be enough, prompting scientists to investigate other options. One of the most ambitious propulsion concepts ever proposed is nuclear pulse propulsion, a technology that involves propelling a spacecraft by detonating a series of nuclear explosions behind it. The basic idea is to release small nuclear bombs or thermonuclear devices at regular intervals, with each explosion providing a powerful burst of thrust. A massive pusher plate at the rear of the spacecraft would absorb the force of the explosions, converting it into forward motion and propelling the spacecraft forward at high speeds. Nuclear pulse propulsion was first proposed in the 1950s by physicist Stanislaw Ulam and later developed into a project known as Orion by a team of scientists at General Atomics, including Freeman Dyson. The Orion project, which operated in the early 1960s, envisioned a spacecraft powered by nuclear explosions that could potentially reach speeds of up to 10% of the speed of light, drastically reducing travel time to nearby stars. The potential of nuclear pulse propulsion is immense, as it theoretically offers far higher speeds than chemical Orion propulsion. By detonating nuclear devices, a spacecraft could achieve significant momentum with each pulse, allowing it to accelerate much faster than with conventional propulsion methods. If perfected, this technology could reduce travel time to Proxima Centauri to just a few decades, making interstellar travel a realistic possibility within a human lifetime. However, nuclear pulse propulsion faces significant technical and ethical challenges. Detonating nuclear devices in space poses risks to the environment and could have severe geopolitical consequences, as the use of nuclear technology in space is restricted by international treaties. The Orion project was eventually cancelled, partly due to concerns about nuclear fallout and the political implications of launching a nuclear-powered spacecraft. Moreover, developing a pusher plate capable of withstanding repeated nuclear blasts without damage remains a daunting engineering challenge. Despite its challenges, nuclear pulse propulsion remains a tantalizing concept for interstellar travel, and some modern adaptations of the idea, such as fusion-based propulsion, continue to be explored. While the original Orion project may have been shelved, its legacy endures, inspiring scientists to think boldly and pursue innovative solutions for traveling to the stars. Another revolutionary concept for interstellar propulsion is laser propulsion, specifically in the form of light sails. Light sail technology involves propelling a spacecraft by directing powerful laser beams at a large reflective sail attached to the spacecraft. The photons from the laser exert pressure on the sail, pushing it forward and gradually accelerating it to high speeds. While the force exerted by photons is extremely small, it is constant, meaning that over time, a light sail could achieve velocities close to a significant fraction of the speed of light. The concept of light sails has gained considerable attention through initiatives like the Breakthrough Stars HOT project, an ambitious effort funded by philanthropist Yuri Milner and supported by scientists including Stephen Hawking. The goal of Breakthrough Stars HOT is to send miniature gram-sized probes to Proxima Centauri using light sail technology. The project envisions a network of ground-based lasers capable of focusing beams on the sails, accelerating the probes to 20% of the speed of light. At this speed, the probes could reach Proxima Centauri in about 20 years, enabling humanity's first close-up study of a nearby star system. Light sails offer several advantages over traditional propulsion methods. Because they do not require onboard fuel, light sails significantly reduce the mass of the spacecraft, making it easier to achieve high speeds. Additionally, laser propulsion is scalable, allowing for multiple probes to be launched simultaneously, each carrying different instruments to gather data. This flexibility makes laser propulsion an attractive option for interstellar missions where rapid, lightweight probes are ideal. However, laser propulsion and light sail technology also face formidable challenges. Creating a laser array powerful enough to accelerate a probe to 20% of the speed of light requires an enormous amount of energy, on the order of 100 gigawatts, roughly equivalent to the output of a large nuclear power plant. Synchronizing and focusing this power over vast distances presents additional engineering challenges. The sail itself must be extremely thin, lightweight, and reflective, capable of withstanding high levels of heat and radiation without degradation. Moreover, guiding a light sail across interstellar distances requires precision targeting to ensure it remains on course. Even slight deviations could result in the probe missing its target star system by millions of miles. A communication with such high-speed probes also poses a challenge, as the data must be transmitted back to Earth across light years, requiring sensitive receivers and robust signal processing. Despite these challenges, Breakthrough Stars Hot has spurred considerable interest and research into light sail technology. The project's ambitious timeline and objectives have inspired innovations in materials science, energy generation, and laser technology, each bringing humanity closer to making interstellar exploration a reality. The development of advanced propulsion systems is essential for humanity's future in space. Each of the propulsion technologies discussed here, ion propulsion, nuclear pulse propulsion, and laser-propelled light sails, represents a significant step forward, pushing the boundaries of what is possible. While each technology has its unique strengths and limitations, they collectively reflect a growing commitment to overcoming the obstacles of interstellar travel. Ion propulsion has already demonstrated its utility for missions within our solar system and may play a critical role in future exploration of asteroids, planets, and moons. Nuclear pulse propulsion, though currently restricted by regulatory and technical barriers, offers a bold vision for high-speed interstellar travel that could one day be revived with further advancements in nuclear fusion. Meanwhile, laser propulsion and light sails hold promise as viable solutions for sending lightweight probes to nearby stars, potentially within our lifetimes. The pursuit of advanced propulsion systems is more than a quest for faster spacecraft. It is a quest to expand humanity's reach beyond the confines of our solar system, to explore new worlds, and to seek out answers to the age-old question of whether we are alone in the universe. With each innovation, we move one step closer to bridging the gulf between stars and realizing the dream of interstellar exploration. As humanity stands on the brink of an era where interstellar travel becomes more than a distant dream, ambitious initiatives like Breakthrough Stars Hot have reignited hope that we may one day reach the stars. Launched in 2016 and funded by tech entrepreneur Yuri Milner, with the involvement of renowned physicists like Stephen Hawking, Breakthrough Stars Hot is an innovative project with a bold goal: to send miniature spacecraft to the Alpha Centauri system, our nearest neighboring star system, within the span of a single human lifetime. Using revolutionary light sail technology and powerful ground-based lasers, Breakthrough Stars Hot aspires to achieve speeds of up to 20% of the speed of light, making interstellar exploration an achievable reality. Breakthrough Stars Hot is part of the larger Breakthrough Initiatives, a collection of scientific and technological programs designed to answer profound questions about life in the universe. With a focus on developing technologies for space exploration, Breakthrough Stars Hot represents humanity's first serious attempt to reach another star system. The Alpha Centauri system, which includes the stars Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, lies 4.37 light-years away, close enough to be within the reach of advanced light sail technology. The primary objective of Breakthrough Stars Hot is to develop a fleet of ultra-lightweight, gram-sized spacecraft called starships, each equipped with a light sail. These miniature probes would be propelled by a high-powered array of ground-based lasers that would direct intensely beams of light at the sails, accelerating the probes to around 60,000 kilometers per second, or roughly 20% of the speed of light. At this velocity, the starships could reach the Alpha Centauri system in about 20 years, an unprecedented timeframe in interstellar terms. Upon arrival, they would collect and transmit data back to Earth, potentially offering the first ever close-up images of an exoplanet orbiting another star. The project's focus on lightweight, high-speed probes addresses the fundamental limitations of conventional space travel, where propulsion systems require large amounts of fuel that add mass and limit achievable speeds. By contrast, Breakthrough Stars Hot's light sail technology allows for a minimalist approach, drastically reducing the mass and energy requirements for the spacecraft itself. This technology could enable humanity's first interstellar reconnaissance mission, potentially answering questions about the habitability of planets in the Alpha Centauri system and expanding our understanding of the broader cosmos. In addition to its scientific aims, Breakthrough Stars Hot seeks to push the boundaries of what humanity can achieve through technological innovation. The project is inspiring advancements in materials science, optics, and laser technology, each critical to realizing its ambitious vision. The endeavor reflects humanity's enduring desire to explore, marking the first steps toward an era in which interstellar travel is not only conceivable but actively pursued. The concept of light sails relies on the fundamental principles of physics, specifically the momentum carried by photons. While photons, or particles of light, have no mass, they do carry momentum. When a photon strikes a reflective surface, it imparts a tiny amount of force. Light sails harness this force to create propulsion with the cumulative impact of millions of photons pushing the sail forward. Though the force exerted by individual photons is minuscule, it is continuous, allowing a light sail to accelerate steadily over time. Were breakthrough stars hot, the star chips would be equipped with a thin, lightweight, highly reflective light sail capable of withstanding extreme acceleration. The light sail must be large enough to catch a significant amount of light from the laser array, yet thin and lightweight to minimize mass. Advanced materials like graphene, which is both strong and lightweight, are being considered for the sail's construction. Graphene's reflective properties and durability under intense light exposure make it an ideal candidate for the demanding conditions of interstellar travel. The mechanics of the light sail involve an array of lasers on Earth directing focused beams of light at the sail, pushing it forward at incredible speeds. The laser array would be powerful enough to accelerate the star chip to 20% of the speed of light within minutes. This rapid acceleration demands precise coordination and control over the laser array, as any deviation in the beam's focus could result in the star chip veering off course. The sail itself must be able to withstand not only the intense laser pressure but also the gradual degradation from cosmic rays, interstellar dust, and radiation over the course of its journey. To achieve the target speed, the sail would need to be extraordinarily thin, on the order of nanometers in thickness, and precisely engineered to optimize reflection. Any imperfections could lead to uneven force distribution, causing the sail to warp or tear under the intense pressure. Additionally, the sail must be capable of withstanding thermal stress, as the focused laser light could generate substantial heat. Materials that are both thermally stable and reflective critical to the project's success. The star chips themselves, while incredibly small, would be outfitted with miniaturized scientific instruments, communication systems, and onboard computing to collect and transmit data. These instruments would need to be robust enough to operate in deep space and withstand the radiation and high-speed collisions with interstellar dust particles. Developing technology to communicate data back to Earth from light years away is another significant challenge, requiring innovations in signal processing and data compression. One of the most formidable challenges for breakthrough stars hot lies in the development and deployment of a ground-based laser array powerful enough to propel the star chips. Known as a phased array, this system would consist of thousands of individual lasers working in concert to create a single, coherent beam directed at the light sail. Each laser must be meticulously synchronized to ensure the beams remain focused over vast distances, as any misalignment could diminish the beam's power and result in inefficient propulsion. The energy requirements for this laser array are staggering. To achieve the necessary acceleration, the phased array would need to generate around 100 gigawatts of power, roughly equivalent to the combined output of several large nuclear power plants. Building and maintaining such a powerful energy source presents significant logistical, financial, and environmental challenges. Additionally, transmitting that energy through the atmosphere without losing intensity is another technical hurdle, as atmospheric distortion and scattering could weaken the beam before it reaches the light sail. To overcome atmospheric interference, breakthrough stars hot researchers are exploring the use of adaptive optics, a technology that adjusts the shape of the laser beams in real time to counteract atmospheric turbulence. Adaptive optics are commonly used in ground-based telescopes to correct for the blurring effects of Earth's atmosphere, and similar principles could be applied to maintain the coherence of the laser beam. However, scaling adaptive optics to accommodate the power and precision required for breakthrough stars hot is a monumental task, necessitating substantial advancements in optical engineering. Once the star chip reaches the desired speed, the laser array would no longer provide acceleration, leaving the probe to coast on its own through interstellar space. At this stage, any course corrections or adjustments would be impossible, making accurate targeting of the laser beam essential during the initial acceleration phase. Even minor errors in alignment could result in the star chip missing its target by millions of miles. The margin for error in guiding the probe over such vast distances is minuscule, and any deviation could render the mission unsuccessful. Another critical challenge is ensuring that the star chips can communicate with Earth once they reach the Alpha Centauri system. Due to the high speeds and vast distances involved, sending data back to Earth presents unprecedented difficulties. The star chips will be equipped with tiny transmitters, but the signals will be incredibly weak by the time they reach Earth. To detect these faint signals, scientists will likely need to develop ultra-sensitive receivers and possibly even launch a series of relay satellites to boost the signal. The time delay due to the distance between Alpha Centauri and Earth would mean that any data sent would take over 4 years to reach us. The sheer cost and complexity of breakthrough stars hot are significant barriers to its feasibility. Developing and maintaining a phased laser array, building the necessary infrastructure, and addressing technical challenges all require substantial funding and sustained commitment over decades. Despite the technical challenges, the feasibility of using ground-based lasers for propulsion remains an active area of research, with promising developments in laser technology and materials science. If successful, breakthrough stars hot would revolutionize humanity's approach to space exploration, proving that interstellar travel is possible. This mission could be the first step in a larger vision of interstellar exploration where fleets of tiny, high-speed probes explore nearby star systems and search for signs of life or habitable planets. The data collected by these probes could answer fundamental questions about the composition of exoplanetary systems, the prevalence of planets in habitable zones, and the possibility of extraterrestrial life. Breakthrough Stars Hot has already spurred scientific and technological progress, inspiring research into materials, optics, and energy management that could have applications far beyond space exploration. The project also represents a philosophical milestone, challenging humanity to think beyond the boundaries of our solar system and consider the implications of exploring distant worlds. By seeking to reach Alpha Centauri, Breakthrough Stars Hot embodies a commitment to exploration that transcends individual lifetimes, inspiring future generations to pursue knowledge and push the limits of human potential. In summary, Breakthrough Stars Hot is more than a technological challenge. It is a testament to humanity's enduring curiosity and determination to explore the unknown. While the journey to Alpha Centauri is fraught with difficulties, each obstacle surmounted brings us closer to a new era of exploration, one in which the stars are within our reach. The quest to explore distant stars has led scientists to imagine and theorize about propulsion technologies far beyond our current capabilities. Concepts like warp drives, Dyson spheres, and antimatter engines stretch the boundaries of what is scientifically possible and offer a glimpse into the future of space travel. While these ideas remain speculative, they represent profound breakthroughs that could transform our approach to interstellar exploration. Each of these cutting-edge concepts addresses fundamental challenges in space travel such as speed, energy, and efficiency, paving the way for potential technological revolutions. One of the most intriguing concepts in interstellar travel is the warp drive, a theoretical technology inspired by Albert Einstein's theory of general relativity. Unlike traditional propulsion systems, a warp drive does not rely on fuel to propel a spacecraft through space. Instead, it manipulates space-time itself, creating a bubble around the spacecraft that allows it to travel faster than the speed of light without violating the laws of physics. The basic premise of a warp drive is rooted in the concept that space-time, the fabric of the universe, can be stretched and compressed. In 1994, physicist Miguel Alcubierre proposed a theoretical framework for a warp drive based on this principle. The Alcubierre drive would contract space-time in front of a spacecraft while expanding it behind, creating a wave that effectively surfs through space. The spacecraft within the warp bubble would remain stationary relative to the space inside the bubble, avoiding the relativistic effects that typically occur at near light speeds. In this way, a warp drive could theoretically allow a spacecraft to travel vast distances at superluminal speeds without breaking the universal speed limit. The concept of a warp drive, while compelling, faces several significant scientific and technological challenges. First and foremost, the energy requirements for creating and sustaining a warp bubble are astronomical. Early calculations suggest that generating the necessary warp field would require more energy than the total mass energy of a planet, rendering it currently unfeasible. However, recent research has suggested that modifying the shape of the warp bubble might reduce the energy requirements to more manageable levels, potentially within reach of advanced civilizations. Another challenge is the need for exotic matter, hypothetical materials with negative energy density to stabilize the warp bubble. Exotic matter does not exist in any known form and would have unusual properties, such as repelling rather than attracting other matter. While quantum theory allows for the possibility of negative energy, it remains unclear how to generate or harness this phenomenon on the scale required for a warp drive. Despite these challenges, the allure of the warp drive continues to captivate scientists and enthusiasts alike. Organizations like NASA's EagleWorks laboratory have conducted experimental research into warp field mechanics, hoping to uncover insights that could one day make this concept a reality. Even if the technology remains far from practical application, the study of warp drives pushes the boundaries of theoretical physics and may lead to unexpected discoveries about the nature of space-time itself. If warp drives were ever developed, they would revolutionize interstellar travel, enabling humanity to reach distant stars within a matter of days or weeks, rather than decades or centuries. The implications for exploration and the potential for contacting other intelligent civilizations would be profound. While warp drives remain in the realm of science fiction for now, they represent humanity's ultimate aspiration to transcend the limitations of space and time, embodying a future where the stars are truly within our grasp. As humanity considers the prospect of long-term space exploration and interstellar travel, the question of energy becomes paramount. Traditional energy sources such as chemical fuel or even nuclear power are insufficient for the demands of deep space missions or the sustained operations of interstellar spacecraft. Enter the concept of a Dyson sphere, a massive structure built around a star to capture and harness nearly all of its energy output. The idea of the Dyson sphere was first proposed by physicist Freeman Dyson in 1960 as a theoretical solution to the energy needs of an advanced civilization. In Dyson's original conception, a highly developed society would require an enormous amount of energy, far beyond what planets could provide. By constructing a series of solar collectors or satellites around a star, this civilization could effectively capture its entire energy output, providing virtually limitless power for technological and exploratory pursuits. A Dyson sphere could take several forms. One of the most commonly envisioned is the Dyson swarm, a collection of solar panels or satellites orbiting a star at various distances, each absorbing and transmitting energy back to a central hub. Another concept is the Dyson shell, a solid or semi-solid structure encompassing the star. However, the construction of a complete shell is often considered infeasible due to the gravitational stresses and material requirements involved. More practical concepts like Dyson swarms or Dyson bubbles, clusters of solar collectors held in place by radiation pressure or gravitational balance, offer more realistic alternatives for energy collection. The energy potential of a Dyson sphere is immense. The Sun, for instance, emits approximately 3.8 x 1026 watts of power. Capturing even a fraction of this energy would provide more than enough power to sustain interstellar spacecraft, massive data processing facilities, or advanced computational simulations. For interstellar travel, this energy could be used to fuel high-powered propulsion systems, maintain life support systems on long-duration missions, or even support the construction of habitats in deep space. Constructing a Dyson sphere, however, presents extraordinary engineering challenges. The sheer quantity of materials required to build a structure on this scale would necessitate resources from multiple planets, or even entire asteroid belts. Advanced robotic technology would be essential for constructing and maintaining the components of the sphere, given the vast distances and hostile environments involved. Additionally, managing the immense gravitational forces around a star and stabilizing the structure's orbit would require precise calculations and control systems. While a Dyson sphere remains beyond our current technological capabilities, the concept has had a significant influence on both science and popular culture. It serves as a benchmark for imagining the capabilities of an advanced civilization and provides a framework for the search for extraterrestrial intelligence (SETI). Some astronomers have proposed searching for Dyson spheres around distant stars as a potential techno-signature of advanced alien civilizations. By analyzing the infrared emissions of stars, scientists may one day detect the presence of artificial structures or energy harvesting technologies similar to a Dyson sphere. In the context of human exploration, a Dyson sphere or swarm would be invaluable for sustaining long-term missions and supporting colonies beyond our solar system. Such a structure would effectively transform a star into an energy powerhouse, enabling unprecedented levels of technological advancement and exploration. Although the construction of a Dyson sphere may remain a distant vision, it symbolizes humanity's drive to harness the power of the cosmos itself and serves as a reminder of the boundless potential of human ingenuity. Another highly speculative yet potentially transformative technology for interstellar travel is the antimatter engine. Antimatter is a form of matter composed of particles that have the opposite charge of their corresponding matter particles. When matter and antimatter come into contact, they annihilate each other, releasing an immense amount of energy in the process. This energy density is far greater than that of chemical or nuclear reactions, making antimatter one of the most powerful potential fuels for propulsion. In theory, an antimatter engine would function by combining tiny amounts of antimatter with matter in a controlled environment. The resulting annihilation would release energy that could be harnessed to propel a spacecraft at extremely high speeds. Unlike conventional rockets, which rely on chemical reactions, an antimatter engine would produce much greater thrust, potentially enabling near light speed travel. With sufficient antimatter fuel, a spacecraft could reduce travel time to nearby stars from centuries to mere decades, making interstellar exploration within a human lifetime more feasible. The potential of antimatter engines is immense, but so are the challenges associated with antimatter production, storage, and control. Producing antimatter requires vast amounts of energy, as it is typically created in particle accelerators like CERN's Large Hadron Collider. Currently, the amount of antimatter produced globally is minuscule, far from the quantities required for propulsion. For example, producing just 1 gram of antimatter would take billions of dollars and decades of work, highlighting the difficulty of scaling up antimatter production. Storing antimatter presents another major obstacle. Since antimatter annihilates upon contact with matter, it must be contained in a vacuum, isolated from any contact with the walls of its container. Scientists have developed techniques using magnetic fields to trap small quantities of antimatter particles, but these methods are not yet viable for the large-scale containment needed for propulsion. Additionally, any containment failure would result in a catastrophic release of energy, posing significant risks for both the spacecraft and its surroundings. Despite these challenges, research into antimatter continues, as the potential benefits could revolutionize space travel. If scientists could find efficient methods for antimatter production and storage, antimatter engines could propel spacecraft to unprecedented speeds, enabling fast missions to other star systems. Additionally, antimatter could serve as an energy source for a variety of applications beyond propulsion, such as power generation for long-duration space missions or providing energy for habitats on distant planets. In recent years, advances in particle physics have spurred some optimism about the feasibility of antimatter engines. Researchers are exploring potential production methods that could reduce the cost and energy requirements, such as using high-intensity lasers to generate antimatter particles. Additionally, advancements in magnetic confinement technology may improve our ability to store and control antimatter, bringing us closer to realizing this technology. While antimatter engines are still in the early stages of theoretical development, they represent one of the most promising avenues for achieving interstellar travel within a reasonable time frame. The immense energy density of antimatter could enable speeds that, while not reaching the speed of light, would allow for significant reductions in travel time. If the technical challenges can be overcome, antimatter engines could mark the beginning of a new era of exploration, where humanity can venture far beyond the boundaries of our solar system. Warp drives, Dyson spheres, and antimatter engines each embody a different aspect of humanity's desire to explore and expand beyond our cosmic backyard. Warp drives offer a vision of traveling vast distances by bending the fabric of space-time itself, while Dyson spheres suggest a way to harness the full power of a star to fuel our technological ambitions. Antimatter engines, with their unparalleled energy density, promise speeds that could make interstellar travel achievable within a human lifetime. Each of these concepts, though currently speculative, represents a different solution to the challenges of space travel, from energy limitations to speed and distance. These cutting-edge concepts remind us that the path to interstellar exploration requires not only advancements in technology, but also a willingness to question the boundaries of what is possible. By investigating and developing these revolutionary ideas, humanity continues to push the limits of scientific understanding and technological capability. Though warp drives, Dyson spheres, and antimatter engines remain far from realization, the pursuit of these concepts drives innovation, inspires generations, and holds the promise of a future where the stars are not just distant lights in the sky, but destinations waiting to be explored. The Alpha Centauri system, our closest stellar neighbor, has long fascinated astronomers and space enthusiasts alike. Located just 4.37 light-years away, it consists of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. This system represents humanity's best chance for interstellar exploration due to its proximity and the tantalizing possibility of habitable planets orbiting these stars. As we push the boundaries of observational technology, Alpha Centauri remains a prime target in the search for exoplanets, particularly those that could support life. Alpha Centauri A and B form a binary star system, meaning the 2 stars orbit each other. They are quite similar to our Sun, making them particularly appealing for the study of potentially habitable planets. Alpha Centauri A is a G-type star, nearly identical to the Sun in size, temperature, and luminosity. Alpha Centauri B, a K-type star, is slightly smaller, cooler, and dimmer. Together, they orbit around a common center of mass, completing one orbit every 80 years. These 2 stars are relatively stable, which is a favorable trait for potential habitability. Stability in a star reduces the likelihood of harmful stellar flares and intense radiation bursts, conditions that can strip atmospheres from planets or disrupt the development of life. The stable environment around Alpha Centauri A and B makes them promising candidates for planets with atmospheres conducive to life, as they could theoretically support a habitable zone, a region around a star where conditions allow for liquid water to exist. Beyond Alpha Centauri A and B lies Proxima Centauri, a red dwarf star that is slightly closer to Earth. Proxima Centauri has its own intriguing exoplanet, Proxima Centauri B, which lies in its habitable zone. However, due to the nature of red dwarfs and their tendency to produce strong stellar flares, Alpha Centauri A and B are often considered more promising candidates for life-bearing planets. The combination of a habitable zone, stable energy output, and relative similarity to our Sun makes Alpha Centauri A and B ideal targets in the search for Earth-like worlds. The search for exoplanets in the Alpha Centauri system has spurred the development of advanced observational methods and instruments, each designed to overcome the immense challenges of detecting planets around distant stars. Detecting habitable exoplanets is particularly complex as Earth-sized planets are small and produce only subtle effects on their host stars. One of the most commonly used techniques for detecting exoplanets is the radial velocity method, which measures the tiny wobbles in a star's motion, caused by the gravitational pull of orbiting planets. As a planet orbits a star, it exerts a slight gravitational force, causing the star to shift back and forth. This shift creates changes in the star's spectral lines, which astronomers can observe as shifts toward the blue end of the spectrum when the star moves toward us, and toward the red end as it moves away. For Alpha Centauri, radial velocity measurements are particularly promising because both Alpha Centauri A and B are relatively close and bright, making their subtle movements easier to detect. Advanced spectrographs like the European Southern Observatory's HARPS, High-Accuracy Radial Velocity Planet Searcher, have been used to observe the Alpha Centauri system with extreme precision. HARPS is capable of detecting shifts as small as 1 meter per second in a star's velocity, enabling astronomers to detect Earth-mass planets within a star's habitable zone. The transit method, which has been instrumental in many exoplanet discoveries, involves detecting the slight dip in a star's brightness when a planet crosses in front of it from our point of view. During a transit, the planet blocks a small fraction of the star's light, creating a temporary dimming that astronomers can measure. By analyzing these dips, scientists can infer the size, orbit, and sometimes even atmospheric composition of the planet. While the transit method has proven incredibly effective, especially for detecting planets around distant stars, it requires precise alignment. For planets in the Alpha Centauri system, this alignment is rare, and as a result, transits of Earth-like planets around Alpha Centauri A and B have yet to be observed. Nonetheless, researchers continue to monitor the system in hopes of detecting a transit event, which could provide valuable data about potential exoplanets in the habitable zone. Direct imaging represents one of the most challenging yet promising methods for detecting exoplanets, particularly those in nearby systems like Alpha Centauri. Traditional telescopes cannot directly observe planets around distant stars due to the overwhelming brightness of the stars themselves. However, direct imaging aims to capture actual images of exoplanets by blocking out the star's light, allowing the much dimmer planet to be visible. Recent advancements in direct imaging technology, particularly the development of high-contrast imaging techniques in coronagraphs, have made it possible to directly observe larger exoplanets around nearby stars. Instruments like the Gemini Planet Imager, P, and the Very Large Telescope Sphere, Spectropolarimetric High-Contrast Exoplanet Research Instrument, have been specifically designed to detect exoplanets around stars close to Earth. These instruments use adaptive optics to correct for atmospheric distortions and coronagraphs to block the starlight, making it easier to observe planets directly. For the Alpha Centauri system, direct imaging holds particular promise. In 2021, astronomers using the European Southern Observatory's VOLT, Very Large Telescope, announced the discovery of a possible planet orbiting Alpha Centauri A, although further observations are needed to confirm this finding. Continued advancements in direct imaging, particularly with the upcoming James Webb Space Telescope and proposed missions like the Habitable Exoplanet Observatory HabEx, could bring us closer to directly observing Earth-like planets in the Alpha Centauri system. The Alpha Centauri system's proximity and potential habitability make it an attractive target for future missions. Achieving interstellar travel remains one of humanity's greatest challenges, but if a mission were to target another star, Alpha Centauri would be the most logical choice. A mission to Alpha Centauri could answer fundamental questions about the prevalence of habitable planets, the diversity of planetary systems, and the potential for life beyond our solar system. One of the most ambitious proposals for exploring Alpha Centauri is the Breakthrough Starshot Initiative, which aims to send tiny, gram-scale probes to the Alpha Centauri system using light sail technology. As mentioned in previous sections, these miniature probes, known as star chips, would be propelled by powerful lasers on Earth, accelerating them to approximately 20% of the speed of light. At this velocity, they could reach Alpha Centauri in about 20 years, offering humanity its first close-up view of another star system. The The star chips would be equipped with cameras, spectrometers, and communication systems to collect data and transmit it back to Earth. While they would be too small to carry large scientific payloads, these probes could capture images of planets, measure atmospheric compositions, and detect potential biosignatures. The success of Breakthrough Starshot could revolutionize our understanding of the Alpha Centauri system, providing insights into its planetary structure and habitability. While Breakthrough Starshot is a pioneering concept, other proposed missions aim to study Alpha Centauri from a distance using advanced telescopes. One of the most anticipated projects is the James Webb Space Telescope, JWST, scheduled for launch soon. Although JWST's primary mission is not to study Alpha Centauri, its powerful infrared capabilities may allow it to detect heat signatures from large planets in nearby systems. Additionally, NASA has proposed a range of next-generation space telescopes designed specifically to search for habitable exoplanets. The HabEx, Habitable Exoplanet Observatory, and LUVOIR Large UV Optical Iris Surveyor missions, if funded, would focus on nearby star systems like Alpha Centauri, aiming to directly image Earth-like planets and analyze their atmospheres for signs of life. These missions would use cutting-edge technologies like stars' hades and advanced coronagraphs to block out starlight, allowing for the direct observation of planets that might otherwise remain undetected. Although human missions to Alpha Centauri are still far beyond our technological capabilities, the possibility of sending humans to our nearest star system continues to inspire scientists and the public alike. The prospect of establishing a human presence in Alpha Centauri's habitable zone, whether through colonies on an exoplanet or artificial habitats, represents the ultimate aspiration of interstellar exploration. To achieve this goal, significant advancements in propulsion, life support, and habitat construction would be required. Concepts such as nuclear fusion propulsion generation ships and self-sustaining life support systems are actively being explored as potential solutions for long-duration interstellar missions. Establishing a human presence in another star system, while speculative, is seen as the next step in humanity's journey to become an interstellar species. Exploring Alpha Centauri has profound implications for our understanding of the universe and humanity's future. By studying potential planets within this system, we could gain insights into the formation and evolution of planetary systems, as well as the conditions that support life. Discovering an Earth-like planet with biosignatures in Alpha Centauri would represent a monumental breakthrough, fundamentally altering our understanding of life in the cosmos. that might indicate the presence of life. The discoveries of GJ 273 billion and LHS 1140b have contributed to a growing list of exoplanets found within their stars' habitable zones. Each of these planets offers unique insights, underscoring the diversity of potentially habitable worlds and raising questions about the range of conditions that could support life. Comparatively, GJ 273 billion and LHS 1140b illustrate two different types of planets that orbit red dwarf stars. GJ 273 billion, with its Earth-like size and closer proximity to Earth, represents a more traditional candidate for potential habitability, although its vulnerability to stellar flares remains a concern. LHS 1140b, as a super-Earth, broadens our understanding of what kinds of planets might host life. Its large size suggests that it could retain a dense atmosphere, providing a stable environment that is more resistant to the hazards posed by its host star. The differences between GJ 273 billion and LHS 1140b highlight the challenges and possibilities in identifying habitable exoplanets around red dwarfs. While both planets exist within the habitable zones of their respective stars, the unique conditions of each system influence their potential to support life. GJ 273 billion may resemble Earth in size and energy receipt, but it may lack a stable atmosphere of the search for extraterrestrial intelligence, SETI, for several decades. Another intriguing techno-signature is the possibility of artificial megastructures such as Dyson spheres, which are theoretical constructs designed to capture the energy out. Despite these challenges, SETI has produced some notable results and continues to drive scientific progress. The WOW signal remains one of the most famous unexplained radio signals in SETI history, demonstrating that unusual signals can indeed be detected. whether any of these distant worlds could support life. By studying the atmospheres of Earth like exoplanets and the habitable zones of their stars, JWST can search for biosignatures that could suggest the presence of life. The telescope's high sensitivity of distant planets, identifying chemical compounds that could indicate biological processes. TESS has identified thousands of exoplanet candidates, many of which are in the habitable zones of nearby stars, providing a valuable catalog for detailed study. The ELT However, if Kepler 22 billion's atmosphere is more similar to Earth's, with moderate levels of greenhouse gases, it could maintain temperatures suitable for liquid water and potentially life. In addition to temperature regulation, large gas giants and smaller, potentially rocky planets. Its presence in an atmosphere suggests that the planet may have a hydrological cycle which could support life if other conditions are favorable. Methane and carbon dioxide are also important targets in atmospheric studies. Methane can be produced by both biological and geological processes, so its detection on an exoplanet can be intriguing. On Earth, a significant amount of methane is produced by biological activity, although it can also be generated through volcanic activity and chemical reactions. When methane is found alongside gases like oxygen, which tends to destroy methane in an atmosphere, it may indicate active biological processes replenishing these gases. Similarly, carbon dioxide can provide clues about a planet's greenhouse effect and climate regulation, which are important for maintaining temperatures conducive to life. surface features, providing insights into weather patterns, cloud cover, and potential biosignatures. Its unparalleled resolution will allow astronomers to observe planets orbiting distant stars, deepening our understanding of planetary diversity and habitability. Both Habbex and Louvoir proposed space telescope concepts the accuracy of atmospheric models, enabling astronomers to make more precise predictions about a planet's temperature, composition, and potential for habitability. Citizen science is expected to play an increasingly important role in exoplanet capital of exploration. By investing in education, supporting scientific research, and fostering a culture that values curiosity and innovation, we can ensure that humanity's journey continues. This journey is not only about finding answers, but also about nurturing the qualities that make us human: our desire to learn, to seek, and to grow. In closing, humanity's place in the cosmos is a complex and evolving question, one that challenges us to reflect on who we are and where we are headed. As we expand our reach beyond Earth, we must embrace the responsibility of exploration with wisdom and humility. The universe beckons, and we must rise to meet its call with a spirit of discovery that respects both the mysteries we encounter and the world we call home. In the quest to understand our place in the cosmos, we find not only answers but also inspiration, meaning, and a sense of unity that binds us to each other and to the stars.